Greetings, AP Chem kids! Here we are with the reaction quotient, or predicting the direction of the change. In last section, we actually figured out how to calculate K, given our equilibrium concentration. So now we're ready to figure out what the reaction quotient is. Reaction quotient, when we're talking about a concentration, is abbreviated capital Q, and basically what Q tells us is how the reaction will continue to equilibrium. It's a fancy way of saying, is the reaction at equilibrium? If it is, Miss Griffith can't spell. That's unfortunate. If the reaction's at equilibrium, awesome. If it's not at equilibrium, what's it going to do to get there? Which is really kind of cool. So how to calculate it? Guess what? It is exactly the same way as calculating K. So here's our generic reaction that we have seen before that we use to calculate K. The only thing different here is that Q is used and we may not be at equilibrium, so it's still products raised to their coefficients over reactants raised to their coefficients. So very simply, it's very easy to do. It's exactly like calculating K. The only difference is that Q might not be at equilibrium. We don't know. That's what we're trying to figure out. So are we at equilibrium or are we not? So the reaction quotient is useful because it measures the progress of a reaction. How close to equilibrium are we? And which way will it shift for us to get to equilibrium? So at equilibrium, K will equal Q. Very simply enough, if Q and K are the same, that means you're at equilibrium. If Q is less than K, the reaction will proceed in the forward direction because we have too few products. Remember, it's a ratio of products to reactants. So if Q is smaller than K, we need to get more products to get our ratio bigger, if you will. So if Q is more than K, the reaction will proceed in the reverse direction because we have too few reactants. Pretty simple. So let's see how this works. Here is an example. Example 15.7. It says consider the reaction and its equilibrium constant at 25 degrees C. I2 plus Cl2 goes to 2ICl. Our K at this Kp is 81.9. A reaction mixture contains Pi2 at 0.114 atm, PCl2 at 0.102 atm, and PICl at 0.355 atm. Is the reaction mixture at equilibrium? If not, which direction will it proceed? So all we've got to do at this point is use Q, which is equal to products over reactants. So we've got ICl raised to the second power over I2 times the concentration of Cl2. Very simply, now we're just going to plug in what we know. PICl is 0.355. We're going to square that. We're going to put that over 0.114, and then we're going to multiply by 0.102. And we're going to plug all this in and see how that relates to that 81.9. So, plugging it in our calculator, we've got 0.355 squared, and we're going to divide that by 0.114. And we're going to divide it again by 0.102. This gives us Q, if I did my math correctly, 10.8. So Q is equal to 10.8. 10.8 is less than K, which is 81.9. So that means the reaction will have to proceed to the right. To the right, or you could think of in the forward direction. Pretty simple, right? Really, it's very simple. You're just using Q instead of K. So the last thing here, for the reaction N2O4 going to 2NO2s, a reaction mixture at a certain temperature initially contains both N2O4 and NO2 in the standard states. If Kp equals 0.15, which statement is true for the reaction mixture before any reaction occurs? So, let's think about that for just a second. So if we look at that, if Kp equals 0.15, which statement is true of the reaction mixture before any reaction occurs? Q equals K, the reaction is at equilibrium. Think that? I don't know. If Q is less than K, the reaction will proceed to the right. Or if Q is greater than K, the reaction will proceed to the left. So what we've got is we've got both N2 and NO2 in their standard state. Kp is 0.15. What do you think is going to happen here? Well, what I would look at is that Q equals NO2 squared over N2O4. Does that make a difference in your thought process? Think about it, and I'll get back to you in the next video. All right, bye.